Hello, everyone, and welcome to today's session on accelerating exploration and production innovation without infrastructure constraints. I'm Srinivas Tadepalli from the AWS High Performance Computing team, and joining me today are Nick Shaw and Tim Lin from SQ. Today, we'll talk about some of the key services when it comes to running HPC workloads on AWS. Later on, our partner SQ will talk about their XWI platform that they have developed on top of AWS, including a recent customer success story. So let's get started. As you can see, high performance computing impacts our life every day across a variety of industries and workloads, be it either the car that you drive, the fuel that you use, in weather prediction, in your retirement portfolio, as well as in drug discovery for the medicines. We have been working with our customers very closely over the past many years, and what they have been really telling us, either from a practitioner standpoint or from an IT administrator standpoint, are firstly, they want to be able to run or conduct their science, engineering, and research in a seamless fashion. They want to be able to collaborate with their colleagues who are located globally in a secure environment. They want to be able to run their results faster because oftentimes they are running hundreds and thousands of simulations. And lastly, they need the ability to innovate without any infrastructure constraints. At Amazon, we follow the process of working backwards. We work with our customers closely, understand their needs, and then work backwards to develop a solution that can solve the challenges. At a high level, our customers' challenges can be put into two different buckets. One is from a technology standpoint, the other one is from an operational standpoint. In terms of technology, our customers want enhanced compute solutions, fast networking that can provide a high throughput as well as low latency, and also fast and scalable storage systems for their HPC workloads. When it comes to the operational aspects, it is around security and data governance, the ability to manage their costs easily, and lastly, the ability to transfer and manage their data. So from a technology standpoint, here is a small subset of the updated portfolio of HPC related services, starting with the introduction of the C5N instances, which is our latest generation of compute optimized instances, Elastic Fabric Adapter, a network interface that provides low latency and high throughput up to 100 gigabytes per second, Amazon FSx for Lustre, which is a completely managed Lustre file system, and also AWS Parallel Cluster, which is an HPC cluster management tool. We also have a number of native AWS services to address the operational challenges around data security and data governance, data transfer, as well as cost and cost management. Let's take a look at what we have around data security and data governance. Services like Amazon Macie and Key Management System enables our customers to control where their data is stored and who can access it. Identity and Access Manager provides fine-grained identity and control access so resources have the right access. Services like Inspector, Guard Duty, and CloudWatch will reduce the risk via security automation and continuous monitoring. When it comes to data transfer, we have a number of mechanisms to move your petabyte scale data from your on-premise infrastructure into AWS. Services such as Snowball, Storage Gateway, Direct Connect, and Data Sync will enable customers to move large amounts of data efficiently into S3, which is the object storage. For HPC workloads, you can have your FSx for Lustre file system sitting on top of S3. Once the job is complete, you can move the data from the FSx for Lustre file system back into S3 and then turn off the Lustre file system. And of course, when it comes to long-term storage, we also have services such as S3 Infrequent Access, S3 Glacier, as well as S3 Deep Archive to store large amounts of data for long term. AWS has the most mature cloud platform. We also provide our customers with the broadest and the deepest cloud platform. We have 22 regions in 69 availability zones. We also have about 216 points of presence with 97 direct connect locations serving customers in 245 countries. At a high level, These are all the services that we offer our customers when it comes to running their HPC workloads on AWS. Starting with data management and data transfer, services include data sync, Snowball, Snowmobile, as well as Direct Connect. When it comes to compute, AWS offers more than 270 types of instances, including the latest generation of processors from Intel, AMD, NVIDIA, as well as ARM. When it comes to networking, AWS offers Elastic Fabric Adapter, which provides 100 gigabytes per second network bandwidth and very low latencies. When it comes to storage, AWS offers services like EBS, which is the Elastic Block Storage, EFS, which is the Elastic File System, S3, which is the Object Storage, as well as FSX for Lustre, which is a completely managed high performance file system. When it comes to orchestration and automation, services include AWS Batch, Parallel Cluster, as well as Engine Frame. And lastly, when it comes to visualization or post-processing, we have services like DCV and AppStream that enable customers to look at their results. These are some of the reasons why customers are choosing AWS when it comes to running their mission-critical HPC workloads. Firstly, we have the broadest and the deepest cloud platform with virtually unlimited infrastructure. We have been delivering innovation on our customers' behalf at the fastest pace, including new services such as FSX for Lustre, EFA, AWS Batch. We have the largest global community of partners and customers. And lastly, we have the most mature cloud platform, particularly when it comes to security, scale, and performance. Our innovation and services has been recognized by the industry leaders, and at the recent Supercomputing Conference, we have won 6 different awards, including the Best HPC Cloud Platform. With that, I'm going to introduce our next speaker, Tim Lin from S-Cube, who will talk about their platform XWI. Thank you.
Thank you, Srinivas. Hello, I'm Tim. I'm the principal cloud developer here at S-Cube. Our company spun out of a research group at Imperial College London in 2015, and we specialize in what's known in our industry as FWI, or full waveform inversion. I'll give a brief technical introduction to what we do, and talk about our journey migrating our high-performance computing workload to AWS. And then my colleague Nikhil will talk about some of the projects that we're able to work on as a result of this. Now, in a nutshell, FWI is a completely data-driven approach that utilizes repeated computer simulations of seismic waves to hone in on an accurate model of subterranean features in a way that's faster and more accurate than humans manually interpreting survey data. The whole thing is actually run as a loop over many iterations, and it's quite similar in concept to what we come to know today as large-scale machine learning. If you take the subterranean properties, and we're talking speed of sound through the different rocks in this instance, then that would be the model parameters that we try to learn by doing repeated computer simulations of how seismic waves propagate through them. Now, one of the issues is that these simulations are very computationally expensive, much more so than your typical convolutional deep networks that work on images, for example. So this whole thing is a large HPC exercise for even the most routine type of jobs that we do. Now, we started out with AWS back in 2017, and we used it. It was actually first to build a web-based real-time visualization tool of our results. Now, we work very hard, and we want to be able to keep track of our FWI results no matter where we are. So that was one of the initial draws of using AWS, and that there's a very mature ecosystem of services and expertise that allows you to quickly build these kind of things. It takes much longer to develop persistent web services like this within the confines of a traditionally managed HPC system. If not harder technically, then at least harder bureaucratically. I think many HPC users wouldn't know what I mean, especially if you're on a shared HPC environment like we do. We started bringing the compute onto AWS when, we started out shuttling data from our HPC system to AWS S3 all the time, but quickly realized that everything would just be much easier if you run the HPC workload on AWS as well. And not to mention that making this move means that we can agree to any amount of project with customers without being bottlenecked by the HPC resources that we have access to. And of course, without any capital outlay. So that's one of the main draws of AWS. So our initial approach was very much lift and shift. FWI is a technique started more than, I say, 15 years ago, before the recent boom in machine learning frameworks. So our main production application is what's in vogue in HPC criticals at the time. So that would be a fairly complicated standalone Fortran program, and which has been in continuous development for 15 years. It's designed to run on HPC clusters, and like most programs of that nature, it uses MPI as the communication library. We started out basically just emulating a traditional cluster on AWS that runs Slurm, just like we're used to, except any compute nodes are obviously provisioned on demand right when we submit jobs. So we used an open source AWS project for this. It's in a list of things that Srinivas mentioned. It's called Parallel Cluster, which will just go and provision exactly this for you, and set you up with a login node at the end. And nowadays, they'll even provision an on-demand Lustre shared file system for you, and that's all managed by AWS. I want to mention that a nice thing about a lot of these tools officially released by AWS is that they're almost always open source, and they're built from the same fundamental AWS services that everyone has access to. So it's actually very easy to modify any of the subsystems that don't work exactly the way that we need them to. And one example of this was to make it work with EC2 Spot instances. Essentially, they are spare compute nodes that AWS operate that aren't exactly being used by anyone right now. And AWS provide them at a substantial discount, but they're liable to be reassigned to another customer with a 2-minute warning. When you need a large pool of them, something like tens and hundreds of thousands of CPU cores worth, like we do, there's a service called Spotfleet that takes care of provisioning all of them up to a targeted capacity, and send notifications when they're ready, and also when any of them are about to be reassigned. So what we did is to wire up some additional AWS services that monitors and notifies the main MPI program that may be running whenever any node reassignment is happening, which will immediately exclude them from the communication ring to prevent any potential communication error from crashing MPI. This then plays in with our existing fault tolerance logic inside the application, which reassigns tasks when workers just time out for whatever reason. And that really enabled a really significant cost savings for us, being able to use these Spot instances in a fairly efficient way. And in fact, it allowed us to remain cost competitive for larger companies with much higher capital expenditure for HPC. Now, another key service from AWS for us is S3, which is their main storage service. It's one of the original AWS services, and it's just really benefited from being in development for over a decade. At first, we're simply just storing our seismic data and result files for visualization from the web app. But we quickly found out that they're actually extremely capable for any kind of distribution or broadcasting type workloads for large binary data. And that's something it's been designed very explicitly to do. Over the past year, we've been gradually phasing out MPI from our main application, and S3 was a key part of that. Since we've been absolutely able to rely on it for broadcasting of data to any workers, and for parts written in Fortran where there's not an easy way for it to interact with S3 directly, which mainly has an HTTP interface. There are many emulation frameworks out there that provide a file system-like interface for these legacy programs. And that's never resulted in any performance issues for us. And in fact, that's another benefit of being on AWS, and that there's a very large ecosystem of tools and utilities that support people that use them. And because S3 is basically doing all the heavy lifting now, all the remaining communication between worker and scheduler nodes are just lightweight metadata messages, and we're able to quickly write some custom networking code for that purpose. Now, if you work with MPI, you'll know that it's almost impossible to add workers to an existing communication group, and that's inherent in its design. So the key benefit of removing MPI is that we're able to add and remove worker nodes as the algorithm progresses, which adds a lot of dynamism and flexibility to the kind of hardware mix that will be most optimal for each stage of the iterations. At the same time, we're also evolving a metric collection and event notification system from parsing logs in real time. And we've been able to build this by taking advantage of AWS Lambda and some of its log aggregation services. What's great is that we don't have to spin up any separate servers to run this thing. All of this was just using AWS built-in services. So this whole thing doesn't really have any running cost when there are no jobs to do. We simply attached a log forwarding program to the standard out from each of the XWI processes when it is running. And we sent them to CloudWatch Logs, which is AWS Logs Aggregation Services. And then we have some simple scripts running in AWS Lambda, and they are subscribed to a feed of these logs. And they basically just take each line and parse them to determine if there are events such as iterations finishing or starting, or errors that happen like crashes or hangs, in which case a notification will be sent, or some other useful information which we then will convert to metrics and we store them for later analytics. To give one concrete use case where this added kind of information and flexibility is useful, is where we have this example where we have a special mathematical regularization that we sometimes apply, and they're specifically for salt body dominated fields. And this tries to roughly differentiate salt bodies in the model and make velocity changes fairly homogeneous throughout. Otherwise, the velocity changes tend to happen only at the boundaries of these large salt bodies. I won't go into the details here, but it's something that greatly benefits from running on a really beefy, really expensive GPU. However, most of our application is CPU-based, so we really don't want to provision GPU and then not use it for a large portion of the runtime. What our latest architecture then allowed us to do is to provision this GPU only when the program is in that exact stage of the iteration. And that's all built by and orchestrated by stuff that's printed out in the logs and are being parsed and turned into events and messages with the system that was running in the background. Okay, so to quickly summarize my part, we've had a lot of successes with this migration, and it's resulted in a more flexible and ultimately more productive HPC development environment than what we've had before. We've been able to make a very gradual transition. We start right away thanks to products like Parallel Cluster using lift and shift, but also as we got more comfortable working with native AWS components, we've had a lot of successes replacing various bits of our giant Fortran application to take advantage of their reliability and performance characteristics. It's really allowed us to do quite a bit more development work than we've imagined we're able to, and afforded us an opportunity to work on some really exciting projects to demonstrate our core competency in the FWI algorithm. So next we'll have my colleague Nikhil to briefly talk about some of that.
This is Nikhil Shah, CEO of SQ. In the last year, working with Amazon Web Services, we've rolled out XWI, the industry's first cloud-native waveform inversion solution for inverting raw seismic field recordings directly into images of a section of the Earth. Today I'm going to show some of the standout results obtained utilizing this increasingly critical technology for detecting and characterizing internal properties of complex structures in the subsurface, reducing turnaround time of Earth velocity model building from months to weeks, whilst most crucially for E&P operators reducing their field drilling risks and costs. What was previously a laborious and error-prone process is now automated thanks to this feedback loop which acts on seismic field recordings and is used to derive a design output in the form of an Earth velocity model. It is based on constructing the cost function at each iteration, measuring how wrong an existing model is, then computing the cost function gradient to give the search direction along which to update that given model, going round the feedback loop, iterating to convergence. The cost function gradient calculation is parallelized across shots. Now we can scale the job by bringing down the number of shots per worker instance down to 1. Resources are provisioned in a dynamic pool of interruptible spot instance types. Spot compute is spare compute resources which AWS makes available at up to 90% discount over on-demand pricing for a given instance type. When any worker from the pool is reclaimed, the XWI MPI-free orchestration layer keeps the iteration going by transferring the workload within the required time frame to another available worker. The gradient calculation in the XWI feedback loop is covered in A, and the gradient conditioning by C and D. Further scale up of the job, putting an outer loop for multi-dimensional parameter searches around the main feedback loop is given in B. This can easily result in millions of cores running simultaneously. Now, utilizing the burstable compute to enhance automated velocity model building in customer applications, we start in the North Sea. This is an ocean bottom survey with recording devices laid out on the seafloor, superior quality low frequency signal, and full azimuthal coverage, illuminating the subsurface in all directions. Now we see a plan view of the 24 cable survey with a computational domain of 12 kilometers by 15 kilometers. The target is a reservoir formation overlain by a gas-filled structure depicted by the white oval. Out of the 1,440 receivers, 1/18 or 80 get utilized per iteration, so 80 iterations are required to pass through the entire dataset once. The velocity update after one iteration is shown here at a depth of 1.2 kilometers, red for positive change, blue for negative change. Here we see the update at iteration 90, beginning of pass 2. Trace fits, depicted by the shade of grey of the dots at the receiver locations, shoot up as a low velocity structure emerges into the result. Now the update at the end of pass 2, as the model continues to iteratively self-improve and refine itself. Now the actual velocity, vertical slice on the left and horizontal slice on the right, cutting through the gas accumulation. What started life as a manually inserted blob transforms itself into a geological structure with fine-scale detail defined by the geometry of gas-filled porous layers and faults. Here we have predicted versus field recorded traces from a shot firing into one of the cables. This is before and after, resulting in a very close fit. This is the outcome of the feedback loop. Now we consider a new starting model with no initial representation of the gas cloud. Still, it works its way to the correct answer. This is using component A in the XWI toolkit, the breakthrough proprietary adaptive cost function, which increases convexity and stability of the optimization feedback loop, enabling it to invert for the complete structure from scratch, broadband recovery with a full spectrum of wave numbers. We now move on to the second application from the northwest shelf of Australia. This is a towed streamer survey where the subset used for testing has a computational cross-section of 26 kilometers by 3 kilometers. There are 5,000 plus shots along 9 sail lines with 20% utilized per iteration. Whilst any number of shots can be allocated per worker compute instance, when you bring it down to 2, it results in an iteration time as short as 30 minutes. Traces from one particular shot cable are shown here as 6 bandwidths through the inversion. Limited low frequencies and reflection-dominated arrivals, these are two fundamental causes of failure for vanilla FWI. Yet with XWI-driven feedback loop, we could achieve this result. Simulations accurately mimicking field recordings from low to high frequency. What does this mean for the velocity model? We take a vertical slice through a central inline intersected by a drilled borehole. There's a blind sonic log in black, and this is used to test velocity values in red. We start with a 1D function for velocity. The inversion puts structure in the model, as we can see, closing the gap with the sonic log. And here we have another 1D start, and we get the same outcome, closing the gap with the sonic log. So we have two starting points, scenario 1, scenario 2. both reaching essentially the same place after iteration 50. Here's a final match, highlighting a kick at a depth of 2.3 kilometers, accurately predicted by the inferred velocity. Now let's switch off the adaptive cost function, keeping everything else the same. We see a deflection away from the sonic curve. The effect known as cycle skipping has caused the misfit to reduce to a spurious minimizer. This has produced an erroneous band cutting across the section, causing a misrepresentation of the subsurface, cause for costly dry holes. Whereas with the adaptive cost function, the inversion succeeds, demonstrating the importance of the core algorithm. So here's the AWI evolution. 1D starting model, Hz model, 4 Hz updated, 5 Hz, 6 Hz, up to 20 Hz. You see we're detecting a thin sedimentary layer in the target zone. When we compare it to the no AWI result, this is what it looks like. Back to the AWI result, what we're resolving is a cemented sandstone seal overlying a porous sandstone reservoir. In summary, by increasing subsurface precision, we're generating business value for E&P operations. We're using high-performance computing on the cloud to do this.